Hello everybody. In the previous lecture, I have just explained how the MaxCut problem is a combinatorial optimization problem and how it becomes a 0-1 variable formulation. And in this lecture, we will see the spin or the classicalizing model formulation with +1 comma -1 variables. In the MaxCut problem, the variables are 0 and 1, but in the natural classical icing model, the random variables will be +1 or -1. So we will see how the mapping of the MaxCut problem can be done with the classical icing model. Now, in physics and in quantum computing, it is more natural to use variables zi, which are basically +1 or -1, and these variables are often called as the spins, right? So let us define this variable zi and how these are spins. So we define zi equal to +1 if it belongs to, because ultimately what we are trying to do, we are trying to map the MaxCut problem to the classical easing model. So therefore that is why we are defining the random variables which are actually part of the classical easing model, and then we will try to relate these random variables which are basically zi's with xi's, which are 0 and 1. Now zi will be equal to +1 if I belongs to subgroup S, and it will be equal to -1 if it belongs to the other subgroup, that means S bar. So there is a slight change from 0-1 combination to +1 and -1 combination. Now for an edge, note that if I and j are on the same side, right, that means if the two vertices of the MaxCut problem are from the same group, then zi into zj will be equal to either, because if the two vertices are from the same group, then both the vertices will have spins +1, or both the vertices will have spins -1. So +1 into +1 will give me 1, and -1 into -1 will also give me 1, right? So therefore, and if they are on the opposite side, I will get the answer to be -1. So this zi into zj will give me either +1 or -1 as the output. But we will consider that edge where the output of the product of these two spins is -1. So that edge can be a part of our maximum cut solution. So therefore, a very nice indicator that edge I comma j is cut. So when it will be considered as cut, if this function 1 minus zi into zj divided by 2. So now you see the spin variable is related to +1 and -1. This is how we are changing it to 0 and 1. So if this function 1 minus zi zj divided by 2 is equal to 0, then they are on the same side. That means zi zj product will give me a value 1. If this is equal to 1, then they are on the different side, right? Then so therefore this will be these I and j values will give me a cut which is a part of MaxCut solution. Hence the weighted MaxCut will now be W, as we also see we have defined this is my cut x. So this is my cut x. Cut x will give me the total weight of a cut, right? So if that weight is maximum, I will term it as the MaxCut. So in the same way, I am trying to find out cut z, which will give me the weight of the uh, weight of the uh, weight of any cut. So hence the weighted MaxCut solution will be first we will find out the cut Z. So this was our indicator expression, indicator function into the weight of that edge. So this will give me a weight. And what is our max cut optimization problem? We have to maximize this cut value. When this summation of the individual cuts of the edges is maximum, so that cut will be called as the max cut, right? So cut Z will give me the weights of all the cuts, right? And how to maximize it? This is the expression to maximize. We will take the maximum value of all the combinations of these Zi variable, and this expression will give me the weights of all the edges. So when this is maximized, that number will give me the max cut optimization solution, right? So therefore, this is the expression which gives me the maximum weight. That means this is the expression which gives me the solution of the max cut problem. If the weight is 1, I will get the maximum number of edges for a cut, and that's the solution of the max cut problem. So let us now try to expand this term inside the summation. So my cut Z will be, let us use this expression, not the optimized expression, but the other expression which gives me the weight of every cut. So cut Z will be equal to, let us expand this expression, summation of Wij by 2, and the second term will be Wij multiplied by Zi and Zj, like this. So this is a constant term. Why this is a constant? Because Wi, these are the weights of the graph. So for a given graph, the weights will be constant. Ultimately, this term will be a constant term. Let us call it C. Now the second term is actually, I have explained in one of the videos about the Hamiltonian that we will get in the classical Ising model. So this term actually resembles the Hamiltonian obtained in the Ising model. So therefore, this term is, let me call this term as Hz, and this is basically Ising Hamiltonian. This is the Hamiltonian which we have to the max cut problem is max cut optimization problem is basically to maximize the weight. But if we try to relate it with the Ising model, this is basically minimizing this Hamiltonian, right? If this is minimum, so I will get maximum value of cut Z. The first term is constant, which is independent of Z, right? So maximizing cut Z, maximizing this is equivalent to minimizing this energy term or the Hamiltonian, Ising Hamiltonian. So maximizing the max cut weight, or maximizing the cut Z, or maximizing the maximization problem in max cut problem is actually the minimization of the Hamiltonian, of the Ising Hamiltonian term, right? Or more standard in Ising form is that we have to minimize this expression minus Ji. This term, we are getting it directly from the classical Ising model, right? With suitable couplings. So Jij is the coupling that I have already explained in one of the videos. So as you can see that we have now established a relationship between the max cut problem and the Ising model. So therefore max cut relates to the, so this relates to the cut value up to an additive constant and minus sign. So let us not worry about this minus sign actually. This minus sign has come from the classical Ising model. So there I explained there also that this negative sign actually is there for the minimization problem. But you have to look into this expression, because looking into this expression we find that maximizing cut Z is actually minimizing this Ising Hamiltonian. So that we have to understand basically. So now we can say that since this is a constant C, this term is C, and this term I have designated it as Hz, which is the Ising Hamiltonian. So therefore I can write cut Z to be equal to C minus Hz. So MaxCut wants to maximize cut Z. Maximizing cut Z means maximizing this term C minus Hz. So that's what is written. Since C is constant, why C is constant? Just explained. I have just explained it also, but uh, let's see exactly what is the reason. Because it depends only on the graph, but not on the random variable Zi or Zj. So therefore, this is a constant. C is a constant term. So maximizing C minus Hz means minimizing this expression Hz, which is the Ising Hamiltonian. Hence, maximizing the cut value is equivalent to minimizing the Ising energy. So this term is basically the energy of the system, which we call as the Hamiltonian. Now from equation 1. So what is equation 1? This is equation 1 from which is giving us the cut Z value. So from equation 1, it is obvious that the cut value and the Ising Hamiltonian energy differs only by a minus sign, because MaxCut Z or MaxCut max of cut Z, that in the maximum cut problem, is actually the minimization of Hz in the classical Ising model. So there is a difference of minus sign only. And a constant term, it does not affect where the maximum occurs. So even if there is a constant in the maximum cut problem, it does not affect where at what point the maximum will occur. So solving MaxCut is exactly equivalent to finding the ground state of the Ising Hamiltonian Hz. Very obviously, I have been able to explain the mapping of the MaxCut problem to the classical Ising Hamiltonian. So it is correct to say that solving MaxCut is exactly equivalent to finding the ground state of the Ising Hamiltonian, because we have to find the minimum energy. Minimum energy basically corresponds to the ground state, the minimum energy state. Hence, MaxCut maps to Kubo, which is quadratic unconstrained binary optimization problems. So Kubo basically defines all these problems of classical Ising model and the maximum cut optimization, because it forms a binary optimization. As I just explained, it is a 0-1 optimization problem, right? Then maps to the Ising model. This MaxCut problem maps to Kubo and then maps to the Ising model. Now let us try to understand the matrix view rather than talking about individual weights or edges. Let us try to see a matrix or a Kubo view. That means the quadratic unconstrained binary optimization, looking in more detail that what are the what are the quadratic terms present and what are the linear terms present in the overall MaxCut equation. So the 0-1 formulation is often written in compact form as a Kubo. This is max of for all the combinations of this bit string x. It is equal to the x transpose, and let's say q is some operator into x plus c. So this term is the quadratic. If you see this expression, if you see this indicator expression, let me just explain. If you see this indicator expression, there are two types of terms. One, this is the kind of quadratic term, and these two are the linear terms, right? So that's why if you look at the Kubo formation of the MaxCut problem, you will see that the Kubo formation also includes a quadratic term and a linear term with some constant, right? So the 0-1 formulation is often written in compact form as a Kubo. So this is our Kubo compact form for some symmetric matrix Q. So if we consider some symmetric matrix Q, so we can write it like this, and a vector C. So C is some constant vector, right? Now from the expression, this expression I am taking it from the MaxCut solution, where we have to maximize this cut x, but what the cut x was equal to summation of the weights and this indicator expression. Now this expression has linear terms in xi and quadratic terms in xi and xj. So let us separate out the linear part and the quadratic part. So the linear part of the sum is, so this is our linear part, weights multiplied by xi plus xj. So this part is our linear part. So we group by each vertex I. So each time vertex I is connected to some vertex j, the term xi appears in the summation through the pair I curly brackets I comma j, right? Formally the coefficient of xi is alpha I. So alpha I is the coefficient of this xi term, which is basically this summation of wij. So the linear part becomes alpha I xi. What I'm trying to, we will see into the interpretation of alpha I, but what I'm trying to see, there are two terms, one is xi and xj. We are considering all the vertices defined by I. And what will be xj? So xj are those vertices which are ending up at vertex I. So we are considering those edges for which the edge starting from all the j indices are ending up at a vertex xi. So let us say we fix I and we consider all the edges which are falling on to I, right? So each time vertex I is connected to some vertex j, the term xi appears in the summation. So this is how we will formulate the linear part. Let me explain once again. For vertex I, so that means we are considering only one vertex, which is I. What we will do, we will sum all the weights. What we are doing, we are since I have replaced this term with alpha I am trying to explain alpha I. So what is alpha I? Alpha I, fixing one vertex with index I, we consider all the edges with weights coming from j, right? So all the vertices with I fixed and we are varying j, so all those edges, that means all the edges are ending up at vertex I. So we are taking the weights of all those edges, we are summing that, right? That will formulate our alpha I. So this will be the what alpha I will then do? Alpha I will then be the coefficient of each xi. So that's what alpha I is. For vertex I, sum all the weights of edges touching I. This is called the weighted degree of vertex I. If the graph is unweighted, of course, if this is unweighted, so alpha I will be the degree of vertex I. Therefore, each vertex gets a coefficient equal to its total incident edge weight. Basically, as I just explained, from where alpha I, that means the coefficient of xi is coming, this is how we will consider all the edges which are ending up at vertex I, and we are summing all the weights, so that will be our coefficient. So why does this coefficient appear? Because in the expansion of this expression xi plus xj minus 2xi xj, the xi appears once for every edge that touches I. Thus alpha I is equal to total weight of all edges connected to I, as I just explained this coefficient. Now what is the full Kubo expression now? After we have separated out the linear and the quadratic term, so we can now rewrite the MaxCut objective as cut x will be equal to alpha I xi minus, so that means this is a linear part and this is the quadratic part. So linear coefficients, so minus, so the quadratic part is coming with coefficient value as minus 2 wij, and the linear part is coming out with coefficient alpha I. So this is exactly the Kubo form. So which we Kubo form is this way we have to act. This is the linear part, this is the quadratic part, right? So we have to maximize this. What I'm trying to what we are looking into this MaxCut problem, we are looking into three things. One is that the MaxCut problem itself. Then we are mapping the MaxCut problem to the classical Ising model, right? And the third formation is the Kubo formation. Although all these three formations are similar, with very minor changes, we can use the classical Ising model, where we have to actually find out the minimum energy of the system or the ground state of the system, because the ground state of the Ising Hamiltonian will give us the solution of the problem. In this way, we can say that MaxCut, though it's an NP hard problem, so since MaxCut has been, we have successfully mapped MaxCut problem to the classical Ising model, so therefore we are able to solve this MaxCut problem in polynomial time. So therefore this NP hard problem, so we have actually found out the solution of the NP hard problem by using the mapping of the MaxCut problem onto the classical Ising model. So that's the approach we will use, and we can take up other problems also. We will try to map the other problems to the classical Ising model, and we will then try to use take advantage of the of finding the ground state of the classical Ising model, because ground state of the classical Ising model actually represents the solution of our problem. In this case it was MaxCut problem, or we can otherwise take any other problem which is an NP hard problem. We can solve it through the mapping of the problem with the classical Ising model. So that's the advantage of the classical Ising model. Now we can take an example also to make Kubo equation meaning clear. So we will take a 4 vertex graph. So these are the edges with weights I have given. So for all the vertices, I will find out the neighbors. So for vertex 1, what are the neighbors? It is 2 also and 3 also. So I can find out the weights, right? So the linear part of the Kubo, so this is my linear part of the Kubo, right? And formal procedure to derive the indicator function is basically, if we use the same expression, same things are being put to explain the MaxCut problem with certain example. Here in the example we are using the 4 vertex graph. Otherwise we are using the same expression, same formulas to find out the solution. But otherwise let me just talk about this expression xi plus xj minus 2xi xj. So a standard algebraic form for x. So what we know what is an XOR gate. Xi XOR with xj can be written like this. So if you open up this expression, if we look at the XOR expression, xi XOR with xj, we can write it like this: xi into 1 minus xj plus 1 minus xi into xj. So if we open up this expression will, the opening up of this expression, which is the XOR expression only, comes out to be our indicator function, right? So indicator function is just an XOR gate basically. So this is the indicator function used in the MaxCut 01 quadratic formulation. And so we have been able to map the MaxCut problem to the classical Ising model. So let us now talk about the quantum uh, quantum quantum, what is the quantum part in the problem. So let us see into this. So replace classical spins by quantum operators. How? In MaxCut and Ising model we use classical spin variables. So we use these classical spin variables in the classical Ising model. They are just numbers, +1 and -1. These are only numbers in our solution. So how we will encode these numbers or these spin variables into quantum variables. So they encode discrete choices such as which side of the cut a vertex belongs to. By saying +1 or -1, we actually are saying that which side of the cut this vertex belongs to. So these spins have no quantum behavior. Actually, +1 or -1, these are just numbers. They are not showing any, we are not, solving this problem. But there does not seem to be any quantum behavior which is coming out of this. So they are just parameters in energy. If you try to understand this Ising Hamiltonian term, it's just the energy that we are talking about, and there are numbers represented by these spin variables. Now, to turn this into quantum problem, we replace each classical spin. So what we do to turn it into a quantum problem, we replace each classical spin. That means this Zi and Zj, small Zi and Zj. We replace each classical spin value Zi with a quantum operator. So we are putting a quantum operator here whose eigenvalues are ±1. So what is that quantum operator whose eigenvalues are ±1? So we will consider the poly Z operator, right? The operator with eigenvalues ±1 is the poly Z operator. This is our poly Z operator. So how the Hamiltonian Ising Hamiltonian will change? It will change it like this, because now we are adding the quantum content, quantum formulation into our MaxCut problem. Now the classical Ising energy problem becomes a Hamiltonian operator. So what is this Zi hat and Zj hat? These are the poly Z operators which will work as the spin variables Zi and Zj. So this Hamiltonian acts as the quantum states. This Hamiltonian, this H cap, will now act on the quantum state and not on numbers. Actually, these Zi's and Zj's, this Hamiltonian was acting on the numbers. But once we have translated the classical spin problem into the quantum problem, so therefore the quantum Hamiltonian or the Hamiltonian operator will act on the quantum states now. So each Zi acts on qubit I. This Zi operator will act on qubit I. A qubit has computational basis state ket0 and ket1, and these states are also the eigenstates of this poly Z operator. So if the poly Z operator is acting on ket0, it is basically plus ket0. If it is acting on 1, it will be minus. So that's the operation. That's how the poly Z operator works. So we identify ket0. If the quantum state is in ket0, it is basically equal to Zi. It is basically equal to saying Zi equal to +1. When the quantum state is ket1, so it is basically equal to saying the spin variable to be -1. So each classical spin becomes a qubit whose Z basis measurement gives ±1. So that's how the MaxCut problem, we started with the MaxCut problem, we brought it to the classical Ising model, we converted it into 0-1 binary formulation, we called it Kubo formation, and then we brought into the quantum operations to make. Now this quantum formation will be translated to the quantum computer, and that's how we can use the quantum computer to solve the NP-hard problem, which is MaxCut problem. And in the same approach can be used for other types of problems also. Thank you very much.